Swayam Prabha. Digital India. Educated India.
Welcome everybody. This is the first lecture of the course on multiphase systems, basically transport phenomena in multiphase systems. My name is Saptarshi Basu. I am a faculty member in the Department of Mechanical Engineering at Indian Institute of Science. And so under this particular course, we are going to cover the basics of multiphase systems. And we will take also some specialized topics under the multiphase systems, like for example, droplet evaporation, droplet combustion, boiling, flow through porous media. So, some specific problems as such. So, initially we will start covering that what are the basic principles of a multiphase systems, what are multiphase systems in general, what are the thermodynamics and the transport governing equations for such multiphase systems. So, basically under this particular course we are going to follow a couple of books. One is the Transport Phenomena in Multiphase Systems by Amir Faghri and Y. Zhang. The other book that we are going to follow is Droplets and Sprays by Bill Shiriniano. So, that will cover the specifics of droplet evaporation and droplet combustion type of framework. So, we will cover these things in the subsequent weeks of this particular course. So, the first lecture of this particular course, we are going to give you some examples of multiphase systems and try to understand that why multiphase systems are so very useful, why multiphase systems are required, and why should we learn about multiphase systems in general. So, if we look at the first slide now, you will find that this is the slide which actually says what are the examples of multiphase systems. So, the multiphase systems in general are basically characterized by two or more phases, and they can have one or more components as well. Now, what do I mean by that? By two or more phases, for example, if you have water and water vapor, say you take a saucer in which there is filled with water and you keep it exposed in an open environment. What will happen is that there is liquid water and then there is water vapor. Okay. So, basically there are two phases, water and water vapor. Okay. So, there are basically two phases in this multiphase system. However, because this is kept open in the environment, air is also another component that is present. So, it is also an example of a multi-component system as well. But if you take the same system and say you place it in a vacuum chamber, that means you have sucked all the air out and you have put a saucer of water inside that vacuum chamber. So, what we will have is that basically liquid water and only water vapor. So, that will be a multiphase system which will be characterized by two phases and one component, because water is the only component that is present in this case. Now, multiphase systems can also involve phase changes. And what are phase change events? Like for example, evaporation, boiling, condensation. Here the phase change happens between liquid and vapor. Let us look at this particular thing. So, you can see that evaporation, boiling, condensation, this involves what we call liquid vapor transition. Then melting and solidification is another state that is possible, that is done between solid and liquid. Sublimation is another phase change phenomena which involves solid and vapor. So, there could be phase changes that could happen in a system like this. Like for example, going back to the example of a saucer of liquid water. Okay. So, this is the liquid water, this is the corresponding vapor phase. Now, if you look at a system like this, water actually evaporates as we all know, that if you keep a pot of water out in the ambient, what happens is that the liquid level starts to come down. So, naturally there is mass transfer that happens from here to here. Okay. So, this is a phase change phenomena in which liquid water is being transferred to the vapor phase. Okay. Now, so this is one example. Similarly, you can have an example, you have a liquid water, say for example, you basically cool this, that means you extract the heat out. What happens is that this water starts to freeze, it starts to form ice. Okay. So, that is a transition in which we can call it solidification, for example, right, because it involves solid and liquid. So, similarly there can be sublimation problems also. Naphthalene, for example, it actually is a sublimate, directly gets converted from solid to vapor. So, multiphase systems, you can all see it has a specific interface structure. What do I mean by interface structure? If you look at the same problem of that liquid water, so this is liquid water, this is the vapor, you can see that the vapor and the liquid phase are basically separated by this particular structure, correct. So, this particular structure is basically what is called an interface. Okay. So, the interface means it is a separating surface, okay, which basically separates the two phases. In this particular case, it is liquid and vapor. Okay. It could be between solid and liquid, it could be between solid and vapor as well. Okay. You have all seen, if you take for example, a droplet and place it on a surface, like for example, when you spill something, right, you can take a droplet out and you can put it on a surface. So, this is liquid, this is the solid surface and this is the vapor, right. So, this is a typical example in which this interface, okay, especially this particular sector, basically is a solid liquid vapor phase contact line. So, this is basically called a 3-phase structure that you form. Okay. So, the multiphase systems based on their interface structures can be dispersed phase, can be separated phase, it can be mixed phase as well, and we will see what each of these things means in the next slide. So, for example, coming back to this particular question, that we said that we have something called separated phase, we have something called mixed phase, and in the next slide I will show you what I mean by dispersed phase. Now, separated phase has basically two phases which are separated by a clearly defined geometrically simple interface. This is a very critical definition. Simple, geometrically simple interface is what actually characterizes a separated phase. In most of these cases, let us look at a few examples, like for example, in the picture that you see over here, the phase change, say here for example, there is a liquid layer on a solid surface, and the liquid layer has got a particular curvature that you see over here, right. Okay. So, this liquid layer is a very clearly defined interface, correct, because this interface is kind of very simple, it has got a nice structure to it, you can almost define it by a functional form. So, examples of such systems will be like film condensation, film boiling, solidification, melting, sublimation. This need not be only liquid layer, it can be liquid layer on a solid surface, solid layer on a vapor blanket, it can be vapor layer in a liquid. So, it can be a variety of things, but the interface that you can see is very simple, it is just a wavy interface. The next example can be, for example, when a liquid jet or a gas jet is coming out into the other phase. Like for example, here if you take this is for example, there is a pipe in which you are flushing in liquid. Okay. So, this liquid jet is coming out in an ambient, say, vapor core. So, this is the liquid, this is the corresponding vapor core. As you can see here also, the interface is nice and simple. Okay. It need not be flat and straight, it is just a nice interface. Okay. Similar things can be seen in a liquid vapor annular flow kind of a system. Okay. Here in this case, the inner part can be a vapor, the outer part can be a liquid. or it can be vice versa as well. So, this example it works for atomization problems, like for example in gas turbines and other applications. This works in the case of film boiling, film condensation, film evaporation, etc. Okay. Similar things can be seen in the other applications as well, not going into the details of that, but you can just read up this particular portion. So, it essentially means the surface, the interface, the separating surface between the two surfaces, two phases are basically a nice and simple geometric interface. Let us look into the mixed phase problem now. Now, the mixed phase problem is a slightly more difficult problem to address. It does have some features of a separated phase, that there is a clearly defined interface, but however, if you look at this particular example over here, what you see is that you do see a clear interface like this, but at the same time you see this additional phases being present inside that particular phase. So, it is like phase within a phase kind of a problem. So, you can see, for example, in this case there are vapor bubbles in a liquid film. So, if I draw it, if I magnify it, so this is initially the liquid phase, this is initially the vapor core, right, as you can see from the example. But however, some of the vapors have manifested itself as vapor bubbles. So, these are bubbles, okay, that are situated inside the liquid core. Okay. So, here it is a typical problem in nucleation. Okay. So, we will come to those kind of specific details later, but here you can see it has a clearly defined interface, but at the same time it has got this particular phase present within the liquid core. So, this is what we call a mixed phase. It has got a feature of the separated phase, as well as we will see, it has got also the feature of a dispersed phase. So, if we look at the next one, in the next slide that you can see, if we look at the dispersed phase problem right now, this has got the most complex interface. Okay. Like for example, if you look at this particular application over here, you will see that this is basically like vapor bubbles. So, these are basically vapor bubbles, okay, in a liquid core. Okay. So, you can see readily from this particular problem, this is a vapor bubble in a liquid core. So, the interfaces are, there are multiple interfaces and the interfaces are complex and they are dispersed within the other phase. So, one phase is basically dispersed in the other. So, the same problem can be also in the other case as well. That means there is now a vapor core and then there are these liquid droplets. And they are used in multiple applications, as we can see, spray cooling, combustors, atomizers. It can be also the other one can be used in chemical reactors and things like that. Okay. It can also involve particulate matter. So, it is the typical example of a solid vapor interface. So, in the solid vapor interface, what you can see is that there are solid particles which are dispersed in a liquid flow. So, there is also the interface is now between a solid and a liquid. Okay. So, the dispersed phase are very complicated. So, this requires special handling and these are very common applications as well. Most of the applications that you will find will have dispersed phase. So, essentially what we can say is that on one end of the spectrum you have the separated phase, nice and easy problems to solve, very well defined interface. On the other side of the spectrum you have the dispersed phase, very complicated, where this is one phase is actually dispersed in another. In between these two things you basically have what we call the mixed phase, which has got characteristics of both the separated phase as well as the dispersed phase. Okay. Like for example, applications like this, if you look at this or the things that I showed you in the last slide. So, it has got features of both the things. Okay. So, And on this side we have written all the applications that these kind of systems you will find. So, there you can see almost all the real systems that are there in the world, right from gas turbine to spray cooling to thermal storage, and we will see some of those applications a little later. You can find that all of them are multi-phase applications, all of them involve liquid, vapor, solid interfaces in some form. Okay. So, the real life problems are all more or less multi-phase in nature. Okay. So, that is the reason why you should study multi-phase flow as well. Okay. Now, an important part of the multi-phase systems is studying the interfacial phenomena, because individually when we just deal with a liquid flow, say for example, and one example of a liquid flow is say flow through a pipe. This is an example that we can relate to each and every spectrum of your lifestyle. Flow through a pipe is say it is a pure liquid flow, and we know the equations that actually govern the flow through a pipe. Okay. Similarly, there are other applications when you can also flow gas through the pipe also. I mean, it would basically be the same. But however, when you actually have two phases involved, okay, you have to not only take into account the liquid and the vapor, or the two phases essentially, but you also need to take care of the interfaces between these two phases. And when you have an interface between these two phases, you have to understand how the interfacial transport actually happens, whether it happens from the liquid to the vapor, or vapor to liquid, or solid to vapor, whatever it is. You have to understand the transport mechanism across that interface. Okay. So, interfacial phenomena is extremely hard, and it is extremely important to study. And if you are looking for that, where are these interfacial phenomena is very useful for, I take an example of say cloud formation. That is a very large scale event. There one of the main thing is an interface. If you take another large scale system like a gas turbine, these gas turbines are basically what powers your where we get all these lights and other things. It can be, this is the same gas turbines that are also used in your aero engines. That means when a flight actually takes off, this is the gas turbine that is used. It is also used for thermal storages. These days a lot of emphasis is on solar thermal energies. So, in solar thermal energies sometimes the energy needs to be stored, okay, because the solar thermal energy is not always present. So, you store the energy that you get out of the sun in terms of something, right. So, that thermal storage is also mostly done by phase changing materials. So, thermal storages also involves multi-phase systems. Then you have heard something called fuel cells also, alternative sources of energy. This also involves multi-phase problems. Heat pipes, which is extensively used in space applications, also uses multi-phase systems. It is basically a multi-phase system. Microfluidics, used in biomedical to pharmaceutical or whatever applications that you can think of. Microfluidics also involves basically droplets, okay, of two different phases. Okay. Surface patterning, the things that you use to generate, say for example electronic circuit boards, okay, or preparing specialized surface say for energy harvesting, those surface patternings also are done using multi-phase framework. Similarly, there are other applications like electronics cooling, there are nuclear reactors, all of these basically involves multi-phase systems. So, all involves physics at the solid, liquid, vapor interface, okay, and we need to know how this interfacial phenomena behaves, okay. And these are some of the examples. This is a combustion application, for example, okay, where you actually have a liquid droplet which is burning in a gas field. You can also have a solid surface which is reacting with a gas phase directly. So, this is solid with gas directly. So, this is also an example of a multi-phase system. Okay. Similarly, you can have like two pure substances are in equilibrium. This always happens, that the water evaporation problem that I showed you, it basically involves liquid water and water vapor in equilibrium. You can also have the pipe flow problem that I showed. If you have two different phases, okay, flowing, you can have a problem like that as well. Okay. So, it is very common to have this kind of a systems, and it is important to understand what happens at those interfaces. let us put it like that. This is the interface, how the heat, mass and momentum gets transferred across those interfaces. So, that is the main purpose of this course as well. So, let us take quickly some simple multiphase systems, okay, and let us give you an idea before we go into the thermodynamics of multiphase systems. So, let us take the first example. Let us take, this is for example thermal energy storage. Okay. Thermal energy storage, as I said, uses latent heat, okay, basically uses phase changing material. What happens over here is that this is the phase changing material, what you see over here. There is a hot fluid or cold fluid, whatever it is, that flows through that inner pipe. If it is a hot fluid, the heat gets transferred to this PCM. This PCM actually changes its phase, and the energy of this particular fluid is actually stored here. Okay. So, imagine if this is coming from a solar tower, and that is the heat transfer medium. You flush this fluid through this pipe, you store basically the energy, which is nothing but the solar energy, into this PCM, but just by melting the PCM. Okay. And similarly, when you want to extract heat out of this PCM, you pass a cold temperature fluid through it, you extract the heat out of the hot PCM, and then you use it for n number of applications like lighting your bulb. So, you can get light, okay, or you can use it for other applications as well. Okay. So, like for powering your home, okay, especially in the rural sectors, this would be particularly important in India, from Indian perspective at least. Okay. So, this has got some major advantages. So, here you can see there is a phase change that happens in the PCM. Okay. So, it changes from solid to liquid and liquid to solid once again. So, naturally you have to know how the heat is transferred across the interface. So, this is a thermal energy storage. This is a big candidate because we actually do a lot of research in this particular area. This is what you see over here is basically a gas turbine. Okay, now the gas turbine is a very complicated machinery. It provides 25 to 30% of the world's power and aviation needs. So, you can see this has been the hallmark of power generation in the world, and it is a very complicated device. We will come to those kind of things later, but if you take a section, a very small section, which is basically this part of the gas turbine, this is where the maximum phase change or the combustion part actually takes place. What happens here, if you take a zoomed in view, you have liquid fuel. Okay, in this case the liquid fuel can be jet fuel or any other type of fuel that is basically injected, okay, in the form of a spray. Spray you have all seen, right? This is the Dio spray, for example, that is like a spray, right? So, this is injected in the form of a spray, okay, like for example here, okay, it is injected in the form of a spray into a hot air stream, okay, into a hot air stream the fuel is injected, right. So, what happens, this is actually the spray means it is a combination of many small droplets, right. If you zoom into this particular area here, you will find that there are many such small droplets. Now, these droplets, what they do is that they evaporate this fuel, right. So, they evaporate, they actually mix with this hot air stream and they subsequently ignite. So, this red colored thing that you see over here is basically the flame. Okay. So, as it burns, okay, that is how you get the power. You extract energy out of the fuel and you convert it to electricity or whatever propulsive power or whatever it is that you want to do with it. Okay. Now, here the main backbone of this particular problem is how do you vaporize liquid droplets into the corresponding vapor form, right. So, it becomes a multiphase problem in itself, right, because it involves interaction of the spray with the flow, it involves evaporation and it involves burning. This is for example a picture which shows how a droplet over here should actually burn, right. This is basically the flame, what you can see over here are basically the flame. Okay. So, it is obvious that the gas turbine is a very big machine, right. So, at the heart of that you actually have a multiphase problem. So, the next thing that we are going from gas turbine, if you are interested, if you are a renewable technology guy, you move on to something which is called fuel cell, right. Fuel cell is an electrochemical device, electrochemical energy conversion device essentially, which converts the chemical energy in the fuel directly to electrical energy. Okay. So, in the core of a fuel cell, it is a very simple mechanism actually. This is the PEM fuel cell actually, polymer electrolyte membrane fuel cell. So, in this particular fuel cell, what happens is that oxygen is supplied into the through the cathode, fuel which is hydrogen or methanol comes through the anode, the reaction takes place, you get heat and you get water and carbon dioxide as byproducts. So, this is basically the mechanism of the fuel cell from a very global perspective. However, if you look at the fuel cell complexities like right over here, what you can see is that the fuel cell is a very complicated machinery. It has got multiple layers, like for example, catalyst layer, gas diffusion layer, the proton exchange membrane. There are passages which are of course like millimeter sized passages through which the gas and the oxidizers or the fuel and the oxidizers are actually passed. Here it involves two phase multi component systems, and it also happens at multiple length scales. For example, here the pore sizes can be of the order of microns, here the pore sizes can be of the order of nanometers even. So, this involves flow through multiple passages. Okay. And at the same time, this fuel, this water that is actually produced is not just produced in gaseous form, it can also condense and it can actually block passages. So, there are n number of issues that are there, and all of these things actually involves two phase multi component transport issue. So, the fuel cell is not devoid of a multi-phase nature of it. Okay. Similarly, there is something called heat pipe. Now, the heat pipe is another device in which you basically it is a passive device. Okay. So, what happens over here is that if you look at the diagram over there is that heat pipe is that you basically have once again a liquid and a vapor interface. What happens over here is that heat is taken out in one section. Okay. So, from the basically the vapor core through the liquid, and after that the heat is resupplied in the evaporator section right over there. Okay. So, what happens is that heat is applied to the evaporator section and is conducted through the wick and the liquid evaporates at its interface with the vapor. In the condenser section that is in this particular section, the vapor releases the heat to the liquid as it condenses. So, this entire transport occurs basically through capillary action. So, the heat pipe is basically a passive device which basically transports heat from one section to the other, and the core of it basically is a multi-phase problem, because there is a liquid layer, there is a vapor layer, and then there is an interface which basically separates the two. In some cases you can also have vapor bubbles forming inside the liquid. So, if you remember the previous discussions, this is almost like a mixed phase here. Okay. So, the heat pipe is one of the key applications in space, because it does not have any moving parts, and it actually is very robust, and it is very simple, and it can actually transport very large quantities of heat. Okay. But this is without going into too much details. This also involves a typical multi-phase problem, as you can see from the diagram over there. Okay. Similarly, you can have other cases in which you can have rapid melting and solidification problems as well. For example, in this case it is a solid is irradiated with a pulsed laser. So, basically it is radiative heating. As soon as the pulsed laser happens, you develop a melt, okay, and this melt front can actually propagate depending on the heating. Forget about these parts right now, because these are not important, we will come across to these parts later. But this is one of the major things that is used in the laser heating of solids and melting of solids or laser metal interaction at very small time scales is an important problem that is there in many of the industries for processing as well as for manufacturing industries. Okay. So, this also involves, as you can see, a liquid solid interface. Okay. So, this entire thing, as you can see over here, okay, also involves this kind of problems. This is for example another problem from our work, which is called surface patterning. What is being done over here is that you basically deploy puddles of liquid or droplets essentially like in the form of a circuit. Okay. It looks exactly like this. Okay. Now, this particular fragment of liquid actually evaporates. This has also of course got functional materials, whatever the thing that is you want to pattern the surface with. This liquid actually evaporates and the pattern gets deposited on the surface in a particular shape and size. Of course, this particular problem, because it involves evaporation, it involves flow like that we have shown over there in micrometer scale. So, this is flow in micrometer per second scale. In the gas turbine, the flows are highly turbulent. So, that the order of the flow is like hundreds of meter. Here we are going into the micrometer range. So, the micrometer flows, micrometer per second flows are there, okay, and it also involves evaporation. As it evaporates, it leaves behind this kind of patterns that you can see over here on the surface. So, you can generate patterns at different scales just by using a liquid template. So, the liquid template over here involves interfacial phenomena like evaporation and flow. So, at this particular point we want to emphasize that we have covered in the first lecture, we have covered that what are the examples of the different multiphase systems. Of course, we have not gone into the details, but we have seen that they can be, these multiphase systems can be extremely complicated, they are very diverse. This is not just one particular area. So, it involves from electronic industry to power generation industry to chemical processing industry to any industry that you can think of. These multiphase systems are unipresent everywhere. Okay. So, it is important to know about the nature of these multiphase systems. To know the nature of these multiphase systems, in lecture 2 what we are going to do, we will start looking at the thermodynamics of the multiphase systems with a little bit of recap of the thermodynamics that you may have learned earlier, and we will particularly look at how it applies to the multiphase systems as such. Okay. So, we end lecture 1 over here. We now will go on to lecture 2 to look at the thermodynamics of the multiphase systems. Thank you.